So to get your Norton current from this, you're going to take this circuit and you're going to redraw it, keeping in your 12 at an angle of 0. Your resistor, which is 600 ohms, or 600 at an angle of 0, 600 plus J0. Your inductor, your XL. And in this central branch you've got a capacitor, C your XC. So for your Norton equivalent circuit, or to do your Norton current, you remove that RL and you replace it with a short circuit. So in Thevenin you leave the terminals open, in Norton you put a wire in between those terminals. And the current flowing through there is your Norton current. And at this point you know that you don't have to work out XL or XC because these are already in ohms. When they're already in ohms you don't have to do anything like that. So what would be a strategy, do you think, to work out the value of that Norton current? So what you could do is you could take this parallel part here, which is this and this in parallel, isn't it? Then add on this, and that would get you the total impedance. From the total impedance you could get the total current, and then you could use a current divider to get IN. You could do that. So if you're working towards, you'd have a kind of Z parallel, if you like, which would be your XL in parallel with your XC. Then you'd have a Z total, which would be your R plus your ZP. Then an I total, V over Z total, and then an I Norton, which would be a current divider, taking your total current multiplied by what's in the other branch over what's in the two branches added together. So why don't you work through that? So this is the working for that first kind of parallel section. So that's just that XL and that XC in parallel. Getting you 600 at an angle of 90, or 0 plus J600, that's in both forms. So I'm going to copy that across to there. And you'd usually expect final answers to be in polar form rather than rectangular form. But I've left that in rectangular form so you can add on that additional 600, that series element, that resistance, and then converted that to polar form. So that would then take you on to the next stage. I equals V over Z. So you do the 12 divided by the 848.53. Okay, so it's going to be something in milliamps.
Yeah.
1414.
Yeah.
So 14.14 milliamps, and your angle again, you've got this same situation, 0 minus 45, so that's minus 45. That gets you your current. If you wanted to convert that into milliamps, still need a bit of space from over there, milliamps. So what you do is you keep the angle the same and you just adjust that magnitude into milliamps. You don't do anything with the current. And then you go on and do your current divider. And it's this current here that you're dividing. So that's your current here. It comes up round, hits that junction and then splits. So you want really the current flowing through this branch rather than the current flowing through that branch. So the opposite branch is always for a current divider, so it's that branch there. And because you're multiplying and dividing, you want that in polar form. So we've got that in polar form on our list. With that 200 an angle of minus 90. Then the two branches added together, so you add and subtract in rectangular. I'll just keep that the same just now. Then that's going to be minus G200 plus G150 gets you 50. It's a minus G, so it's 50 at an angle of minus 90. So now you can multiply and divide the magnitudes, add and subtract the angles. It's a bit blurry today.
Or is it XE or XL?
Sorry?
C in the IN, is the formula IT times XL over XL plus XE?
It's the opposite branch for a current divider. So XC goes in the top. So in a voltage divider you use the one you're interested in a current divider you use the opposite one. Minus 90 plus 90. So they are the steps that you take to get your Norton current, and they're kind of your final answers for each of the stages. So when you work out your Norton impedance, short out the supply, resistor's the same, inductor's the same, capacitor's the same, and you essentially pretend that the supply is over here. So it's always described as if you're looking in from that side. And when you're looking in from that side, you'll see the parallel section has changed. So the parallel section is now this section here, and that's in series with that. So to work out your Norton impedance, you'll have a ZP. It's not the same as that ZP, so you can't just copy it across, because it's now this R in parallel with XC. And then your Z Norton, which is the same as your Z total, is going to be that ZP, the one in this half, added on to your XL. And that would be your kind of two stages to get that.
Well, I said ZP and I got minus 108.
Right. Okay.
Minus 81.47.
So these are my two kind of mid-stage answers here, and my working for ZP is this working here. So let's have a look.
What's wrong? 79?
I can put that up next to that. So that's the resistor in parallel with the capacitor. So 600 at an angle of 0 in parallel with 200 at an angle of minus 90. That's right. Over 600 minus J200. That's the top half multiplied out. So the numerator multiplied out. The denominator converted into polar form.
Oh, yeah, I see. I've got
And then you would go, I see, 90 minus minus gets you that.
That's well, I've got that.
Aye, that's what I've got.
And then I've converted it back into rectangular form, so I can add it on, and I've got that 67.08 at an angle of minus 26.56
Yeah.
as my final answer.
Yeah, I've got the same like, number.
So when you do your Norton equivalent circuit, you're going to put these two values in. So your Norton equivalent circuit, that's the structure. So you put in your 0.05656 at an angle of minus 45 as your current. Then for your impedance, you've got your Norton impedance there. Let me arrow in because it's too big. So that's what you're looking for there. And then if you want to get the current through there, or the voltage across there, we'll probably do a current divider. So to get the current through the load, you do a current divider on your I Norton times your Z Norton over your Z Norton plus your RL. And then once you've got your value for that, to get your VL you do IL RL. And it could be ZL obviously, wouldn't make any difference. So that's your working for how you get the current through the load, so hopefully you've got something similar to that.
What's the angle?
Minus 61. Your rounding might be a wee bit different.
I'll do it 60.9 anyway.
That's fine. And then if you remember last week, I think there was a question where it asked you for S, apparent power. So if you remember, the formula for S is V times I, but you would just use the magnitudes. Yeah. So if you're doing S, ignore these angles and just do the magnitude of the voltage times the magnitude of the current. I think that came up in one of the questions last week. And it's apparent power. Not measured in watts, it's measured in VA. Although in this occasion, because it's a resistive load, there would be no Q. There's no reactive power. So your P would be the same value as that.